All right, so we'll go on for Lewis structures for covalents, which are way more common than ionics. First of all, what you're going to do for a covalent, which are, two or more nonmetals, you're going to add up the total number of valence electrons from all members of the molecule. So have your periodic table out. So, for example, carbon, CH4, carbon is in group 4, so 4. Hydrogen in group 1, and there are 4 hydrogens, so 4. We have a total of 8. Do that first for every single one. The second thing you're going to do is draw in bonds, and you're going to use 2 electrons per bond. Now you can draw in dots. What tends to happen is a line is drawn, but just remember that there are 2 electrons per line. So I've just used up 8 electrons to bond, and really only had 8 electrons to start with, so let's see what happens. Now we're going to try for some symmetry. So when you're showing how to put these out, try to make it look symmetrical. Now, third step, you're going to add up how many electrons you used to bond and any leftover electrons you're going to use to satisfy the octet. Octet meaning 8. And why 8? Because noble gases have 8, and everyone wants to become like a noble gas. So for every atom except hydrogen, hydrogen only wants 2 because it's going to be like helium, and helium is only 1s2. So the first energy level has 2, and that's it. Now, what you've seen here is we've used up 8 in bonding, and we only had 8 to start with, so we have 0 left over. So we hope everybody's happy. And it turns out if you look at carbon, it has 2, 4, 6, 8 around it. It's happy. And each hydrogen has 2 available to it, so it's happy. That's our Lewis structure. So if you have exactly enough electrons to bond and satisfy the octet, 2 for hydrogen, you've drawn the right Lewis structure. So CH4 looks like. So let's go ahead and try some more. Carbon is in group 4, fluorine's in group 7, and there are 4 of them. So we are looking at 32 electrons. Do that first. Now carbon, we're going to go ahead and put fluorine, 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 and fluorine. Now we've used up 2, 4, 6, 8 in bonding, leaving us 24 electrons. Now we have to use those 24 to satisfy the octet. Now carbon's satisfied. It has 2, 4, 6, 8 around it. It's good. But each fluorine only has 2, so it's going to need 6 more. So I'm going to give that one 6, that one 6, that one 6, and that one 6. And you see 6 times 4 is 24. I've used them all. So that is the correct Lewis structure. Everything is satisfied. I don't have any leftover electrons. I didn't use too many electrons. It was perfect. Nitrogen is in group 5. Hydrogen's in group 1, and there are 3 of them, 8 electrons. Now we're going to go ahead and bond everything together. 2 electrons per bond. I've used 6. I have 2 left over. Now the hydrogens are fine. The nitrogen only has 6 around it. It will take those 2 and now be happy. Water. Oops, got ahead of myself. After I told you not to do that. All right, water has hydrogen in group 1. There's 2 of them. Oxygen in group 6. We have 8 electrons. I'm going to go ahead and bond those. I've used up 4, leaving me 4 electrons. Hydrogens are happy, but oxygen only has 4 around it, so we're going to give him the additional 4, and that is the Lewis structure for water. Sometimes we will not have enough. That's why we have to be careful. So we're going to try a double or a triple bond. Don't go too fast. Try a double. If that doesn't work, try another double or a triple. So SO2, sulfur's in group 6. Oxygen's in group 6, and there are 2 of them. We have 18 electrons. So I'm going to go ahead and try that. I've used up 4 to bond, leaving me 14 electrons to make everybody happy. And if you see, that will not do it. I need 6 here, 4 here, and 6 there. I don't have it. So what I'm going to do is I'm going to go back. I'm going to use a double bond. So now 2, 4, 6 are being used for bonding. I only have 12 left over to satisfy the octet. So you might be thinking we had 14 over here. How's 12 going to do it? But let's take a look. Sulfur has 2, 4, 6 around it. It only needs 2 more. And this oxygen needs 6 more. And this one only needs 4 more because it has those 4. So that's 12. 2, I'm going to do some different color, 2, 4, 6, 8, 10, 12. So that's the Lewis structure, as messy as that is. SO3, we have 6 plus 6 times 3, we have 24 electrons. All right, so we're going to go ahead and see if that does it for us. I'm using up 6 to bond. I have 18 electrons left over. Well, if you look at this, that won't be enough. We need 20. We need 2 on the sulfur. We need 6 each on the oxygen. That's 20. We don't have it. So we'll try a double bond. So 2, 4, 6, 8 is being used in bonding, leaving us 16 electrons. Now, you say again, I had 18 and that didn't work. How's 16 going to work? But look, sulfur's happy. It's got 8 around it. It's good. This oxygen on top has 4. It needs 4 more. They each need 6. But that's 12, 14, 16. That's it, 16. So that's the Lewis structure. Now you should try on your own CO2 and HCN. CO2 is going to end up looking like that. And HCN is going to end up looking like that, but prove that to yourself. Polyatomic ions, all you do with a polyatomic is you add electrons because that -2 came from the fact that you gained 2 electrons. If you have one with a positive one, you just take an electron away. So sulfur is 6, oxygen is 6, and there's 4 of them. Plus, I'm going to add that 2 from the fact that it's a -2. So we have 32 electrons, and now everything else is the same. I'm going to bond them. Use up 2, 4, 6, 8 in bonding. We need 24 electrons. Sulfur's happy. And after I use those 24 electrons to give each oxygen 6, they'll be happy too. No need for a double bond. Last thing we do with polyatomics is we put a little bracket and put their charge outside of it, but that's the only difference. You should try it for those, or actually just do your homework and that'll be in there. All right, not all molecules will work. There are some exceptions to the rule. Boron will actually do 6. Fluorine should have lone electrons. But it's not, that common. Most of the time they're all going to want 8. And beryllium will actually do 4, just a little. Resonance, please look at page 461 to show examples. It's just that if there's a double bond, it could go between any 2 atoms. You draw it all possible ways. So you'll see the 3 different pictures there. Molecular structure, the valence shell electron pair repulsion theory, they're going to get as far apart as they can in 3-dimensional space. I'll explain that a little bit. All right, make sure you realize that an electron cloud is a lone pair of electrons. It could be a single bond, it could be a double bond, or it could be a triple bond. Now I know these look very different. They're all called electron clouds or steric number. If there's a little cheat sheet that you should have picked up and it says steric NO number, those are what I'm talking about. Those are the clouds. And you're definitely going to want to have that little cheat sheet because it tells you all the different things we're going to go through in the shapes. We count the electron clouds that are bonded versus those that are not bonded. All right, the first one we're going to look at is a tetrahedral. That is when you have 4 clouds, so draw a good Lewis structure. You have 4 clouds around the central atom. They're all bonded. They have a bond angle of 109.5 degrees. I know that looks like 90. Build them in 3-dimensional and you'll see they can do better in 3-dimensional. They can get further apart, and that's 109.5. The next one is if we have 4 clouds and 3 are bonded and one's a lone pair. So we have 1, 2, 3, 4 clouds. 3 are bonded, one's a lone pair. We are still under steric number or electron clouds of 4. And so it has sort of a tetrahedral geometry, but its real shape is called, or molecular shape is called a trigonal pyramidal. Bond angle of 107, a little less because that lone pair kind of spreads out and pushes. Going on with 4 electron clouds, 2 are bonded, 2 are lone pairs. That would be like water. And again, you definitely want to build these. But that's 4 clouds, 2 are lone pairs, 2 are bonded. This is a V-shape or bent bond angle of 105. And again, you're going to want to build that or visualize it. So those are the 3 of the 4 clouds that are on your cheat sheet. So you should kind of follow along there. Then we have our 3 clouds all bonded. So this would be something like that. You'd have 1, 2, 3 clouds around the central atom. They actually, because this is only 3 clouds, can get 120 degrees apart. This is called a trigonal planar. We also could have 3 clouds and 1 is a lone pair and 2 are bonded. And so you see 1, 2, 3 clouds around that central atom, 2 are bonds, 1's a lone pair. That gives you a V shape also, or bent or angular. But the angle's a little different. It's a little less than 120. Again, you should follow along on that sheet. The last one that we're going to look at is 2 clouds around the central atom. That's one of our exceptions. Here's a real common one too. Carbon dioxide. We have 1, 2 clouds around that central atom, 180 degrees apart. All right, giant molecules, you can look within the molecule and see different shapes. So like here, they don't do whoopsie. They don't do the lone pair, but it's there. So we could look at this and say 1, 2, 3, 4 clouds around the central atom, 3 are bonded, 1's a lone pair. That's a trigonal pyramidal. If we go down here, we see there's 1, 2, only 3 clouds around the central atom, all are bonded, trigonal planar. Looks like we have another trigonal pyramidal here with that lone pair, trigonal planar. Now this one's kind of interesting. This is this has a lone pair on it. I just don't draw that in. And you see 1, 2, 3 clouds around the central atom, 2 are bonded, 1's a lone pair. This is a V shape or bent or angular, a little less than 120. These right here, these CH3s, if we were to draw out each individual H, what we'd find is that there are 1, 2, 3, 4 clouds. They're all bonded. This is a tetrahedral.